Welcome to Empowered Learning. This is the second video in the video series on hyperbolic functions. So in the part one video, we went through what the actual hyperbolic function is. We talked a little bit about the arguments or the variables or the independent variables of the hyperbolic function and made sure that we understood that that meant the sector area that was formed with the x-axis, the ray that would go out from the origin to the point on the unit hyperbola, and the graph of the unit hyperbola itself in quadrant one. And of course, we need to make that difference in between those types of arguments and the arguments that we get for trig functions, which are just those angles. So we talked about the similarities and differences of that. We also established what the sine hyperbolic, cosine hyperbolic function was, and used a similar strategy that we would in trigonometry to establish the other basic hyperbolic functions. And then from there, we talked about the graphs of these functions. We talked about not only the graphs, but the inverse of those graphs, as well as several identities. And then we also talked about establishing the derivatives and integrals for all these types of functions. So I'm stating all that to say is that if you are watching this part two video and you haven't watched the part one yet, and you're not familiar with things like what is the derivative or what are the most general antiderivative of our basic hyperbolic functions, you may want to go back and look at that and skim over that video to get all those things before moving forward. We also talked about how to rewrite our inverse hyperbolic functions in terms of logarithm functions. So again, you probably want to go back and look at that just to see what those particular things are before moving forward in this video. So in this video, we're actually just going to do examples using what we learned from the part one video. So here's our first problem, and we see that we're given a value of cosine hyperbolic, and we want to use this identity here, cos squared minus sinh squared, to find the other 5 hyperbolic functions that we need to look for, okay? So since we already have cos x, we know that we need to look for sinh x. We're going to need tangent hyperbolic. We're also going to need cosecant hyperbolic, secant hyperbolic, and cotangent hyperbolic of x. So to start off this process here in finding sinh of x, of course we can use this identity here. So if we use it, then let me get my pen working here. So if we use it, then we know cos squared is just going to be 25 minus 24 squared minus what it is, the square of what it is that we're looking for. And that will equal 1. Okay. So here what this means is if we rearrange this equation sum, we'll see here that we end up having 25 over 24 squared minus 1 is going to be equal to sinh squared of x. And of course here, if we take the principal root of both sides, have this situation here, and if we did that, of course this right hand side here would be absolute value, but since everything that we're doing, we're operating in quadrant one, that would essentially just make our absolute value signs go away, and we would just be dealing with sinh x. So we only have to deal with the positive part of this. So all we have to do now is calculate what is the square root of 25 squared over 24 squared minus 1. All right, so from here, we know that 25 squared would be 625, and 24 squared just so happens to be 576. And we would want to subtract that by 1, but we're going to write 1 as 576 over itself. And then, of course, we'll take the square root of that. And then this turns out to actually end up being square root of 49 over 576. And of course, square root of 49 is just 7, and square root of 576 is just 24. So we see that sinh of x is just going to be 7 over 24. And so now that we have that information, pretty much everything else is relatively easy to come up with. So we know that tangent hyperbolic is just going to be sinh over cosh, and that's just going to be 7 over 24 divided by 25 over 24, and that simply just ends up being 7 over 25 once we work all that out. We know that cosecant hyperbolic is just going to be the reciprocal of sinh hyperbolic, so that'll be 24 over 7. Sesh hyperbolic is going to be the reciprocal of cosine hyperbolic, so that's going to be 24 over 25. And then cotangent or coth hyperbolic is, or coth of x, yeah, as you say it like that, that's just going to be the reciprocal of tangent hyperbolic, which is just going to be 25 over 7. So that is it for those problems. I know there is another way that I know I like to work these problems that kind of uses the same kind of thinking as we do when we do these kind of things in trigonometry. And so here, if we think of a right triangle here, and let's say our angle, even though it's not really that, is x, we know that sine is going to, cosine is going to be adjacent over hypotenuse. And so here, the idea is that we know that cosine squared minus sine, cosine hyperbolic minus sine hyperbolic is going to be 1. And this right triangle here, if we kind of violate the rules a bit and use it with this unit hyperbola, will kind of go along with this. So for a normal right triangle, if we have sides that are 25 and 24, then we know that the other side is 7. Okay. And it works out that, of course, if we plug in, let's say 25 for cosine hyperbolic, and we plug in, and we let, I guess, this 1 that's right here, if we were to replace this with that, because essentially this 1 here would mean if I was to divide everything by 24, so it would look something like this here. So to use it in its pure form, I would have to have this be 1 and have it look like that. And of course, if I did this squared minus that squared, I would end up getting 1. So it all works out. But the thing that I'm trying to get across here is that if we look at this as a right triangle here, we know this side is 25 and that side is 24. We know that 7, 24, 25 is one of the combinations for all the sides of a right triangle. So we could kind of exploit that here. Okay. Not necessarily to use, but I do find it to be helpful to do it when you kind of want a shorthand way to get this done. All right, so next we're going to take some expressions that we have that are written with hyperbolic functions, and we're going to simplify them. And so this first one here, I've already worked out. We just want to figure out what cosh of 3x plus sinh of 3x quantity squared is going to be. And you notice here I've taken both cosh of 3x and sinh of 3x and have rewritten it in exponential form, added the functions together as need be, and then do the simplification, and I see that all that just ends up being an e raised to the 6x. And so the next example we're actually going to work out together. We're actually going to go through this whole process here instead of just me showing it to you. All right, so for this next example here, we want to simplify this expression, which is really the sum of two composite logarithm functions. And the first thing that we note here is that we have natural log of something plus natural log of something else. And we know per our logarithm properties that we can multiply both of the expressions that are inside the separate logarithms like this to make it one logarithm. So here, we could just multiply all this together. So we'll have this. And the fortunate thing for us here is that since this is like a plus b times a minus b, we know that when we multiply this, this is just going to be a squared minus b squared. So we'll write the equivalent of that here. So this will just be cosh squared minus sinh squared. And if you remember, cosh squared minus sinh squared is one of our basic identities. So going back to the part one video notes here, we see that cosh squared minus sinh squared is just equal to 1. So we can use that here. So all that is inside the logarithm is just 1. And of course, we know natural log of 1 is just 0. So that would be the answer for simplifying this expression. So for our last example with simplifying expressions here, we see that we're given this equation, tangent hyperbolic of x is equal to 3 over 5 or 0.6. And what we want to do is figure out what x would actually be. And so here, notice that we have rewritten tangent hyperbolic in its exponential form. And so from that, that means that we're essentially just solving this exponential equation. And to start that process off, here we can just cross multiply here across the equal sign as a quick and dirty way to kind of get everything on the same level, which we have that here. Once we have that, then of course you see here I'm distributing the 5 to both terms on the left side, distributing 3 to both terms on the right. And then I'm situating everything to where I'm going to have all terms with e raised to the x on one side and all terms with e raised to the minus x on the other. So this next step here, that is exactly what I've done. Once I combine like terms, I see I have 2e to the x equals 8e to the minus x. And so I've rewritten this in sort of a ratio fraction form so that I can again do cross multiplication across the equal sign to get everything on the same level. And once I do that, I see I have 2 times e raised to 2x is equal to 8. Divide both sides by 2. And then it becomes just this simple exponential equation to solve. And from there, you could take the natural log of both sides here. So let's say if I did natural log of this and natural log of that, then I would end up getting what I have here, which is just 2x is natural log 4. And then from there, it just depends upon how far you want to go to simplify it. But the answer is either 1/2 of natural log of 4, or you can express it just as natural log of 2. So that would be your final answer for that one. So this will conclude this part 2 video on examples for hyperbolic functions. The next video that I'm going to do, we will talk about finding derivatives of hyperbolic functions, as well as some inverse hyperbolic functions as well, before we get into also doing integrals of hyperbolic functions. All right, I'll see you in the part 3 video.